Since midnight on April 12, 2026, the floor of the Pacific Ocean has been shaking, not once, not twice, 18 times in 12 hours and counting. The largest of these earthquakes measured magnitude 4.2. And that number, that quiet, almost polite number, is precisely what makes this moment so deeply unsettling. Because here is what you need to understand before we go any further. A magnitude 4.2 earthquake at the Juan de Fuca Ridge is not the story. A magnitude 4.2 earthquake at the Juan de Fuca Ridge is the first sentence of a story that geologists have been dreading for decades. A story written not in ink, but in magma, in pressure, in the slow grinding motion of tectonic plates that have been locked against each other for 326 years and are coiling tighter with every passing second. But that is not even the real story. The swarm of earthquakes happening right now, 250 miles off the coast of Washington state, at a depth beneath a frigid and lightless ocean, is not an isolated curiosity. It is a data point inside a system so large, so interconnected, and so far beyond human scale that the scientists who study it speak in careful, measured sentences. The kind of careful, measured sentences that, if you listen to them closely enough, carry their own warning. The Juan de Fuca Ridge is not simply a crack in the seafloor where plates pull apart and small earthquakes rattle in routine clusters. It is the birthplace of a tectonic plate. It is the engine that drives an entire section of Earth's crust eastward, directly into the underbelly of North America, at approximately 4 centimeters per year. 4 centimeters. The width of 2 of your fingers pressed together. That is how fast the Juan de Fuca Plate moves. And every millimeter of that movement, accumulated over centuries, is stored as strain energy in a fault system called the Cascadia Subduction Zone, a 1,000-kilometer-long megathrust fault that the geological record shows has ruptured before, catastrophically, and will do so again. The earthquake swarm happening at this moment is not happening at the Cascadia Subduction Zone, but it is happening at the machine that feeds it, and that machine appears to be waking up. The Juan de Fuca Ridge runs approximately 500 kilometers from north to south through the northeastern Pacific Ocean, and it is not quiet by nature. This is a divergent plate boundary, a place where the Pacific Plate and the Juan de Fuca Plate are being pulled apart by the slow convection of Earth's mantle below. As they separate, hot rock rises to fill the gap, cooling into new oceanic crust at a rate of roughly 6 centimeters per year. What you are watching, in geological terms, is the construction of a new seafloor. And that construction process involves heat, pressure, molten rock, and the kind of seismic activity that has in the past preceded submarine volcanic eruptions. The Pacific Northwest Seismic Network confirmed on April 12th that the swarm is not occurring at the Axial Seamount volcano, the most famous and most monitored underwater volcano in the northeastern Pacific. It is occurring elsewhere along the ridge. And that distinction matters enormously because the history of this ridge is a history of earthquake swarms that were later confirmed to be the signatures of magma moving through the crust, of dikes injecting into the seafloor, of new volcanic material being extruded in events that no human eye has ever directly witnessed. In June and July of 1993, a swarm of earthquakes was detected along the coaxial segment of the Juan de Fuca Ridge using a network of military hydrophone arrays originally designed to track Soviet submarines. The earthquakes migrated 60 kilometers along the ridge crest in a pattern that researchers described at the time as consistent with a lateral dike injection, magma forcing its way sideways through cracks in the crust, pushing the rock apart from the inside. Oceanographic cruises dispatched to the site confirmed what the hydrophone data had implied. An eruption had taken place. Scientists sampled fresh lava flows and discovered event plumes, massive columns of superheated mineral-saturated water rising from the seafloor like underwater thunderclouds. Then in February 1996, at Axial Volcano, further south on the ridge, 4,093 earthquakes were recorded over 34 days. The seafloor vented, lava flowed, microbial communities were scorched, and then, within months, returned. And in September 2001, in the Middle Valley segment, 14,215 earthquakes were detected over a 25-day period, 14,215 earthquakes in less than a month. What you are hearing right now, with 18 earthquakes in 12 hours, is quiet compared to that. And here is where this story becomes genuinely alarming. It may not stay quiet. The question seismologists are careful to say they cannot answer, but that their careful language carries its own warning, is whether this swarm will grow. Harold Tobin, speaking on April 12th from the Pacific Northwest Seismic Network, said the swarm had been superactive since midnight, and acknowledged that it is not possible during a swarm to determine whether it will lead to larger earthquakes. He described the events as relatively common in this type of setting, and he is correct. He also described them as occurring in clusters, which is also correct. What he did not say, what no seismologist will say because precision is the most important tool in their discipline, is that relatively common and harmless are not the same thing. History has confirmed this distinction more than once, and geology has confirmed it far more than that. The monitoring infrastructure in place along the Juan de Fuca Ridge is, by any measure, extraordinary. The U.S. Navy's sound surveillance system, originally a Cold War apparatus of hydrophone arrays strung across the Pacific seabed, now serves as one of the primary detection networks for seismic and volcanic activity along the ridge. The Ocean Observatories Initiative regional cabled array, operated by the University of Washington, extends over 60 miles of submarine cables with more than 140 real-time monitoring instruments, making it the most sophisticated undersea observatory on Earth. These instruments can detect the smallest micro-earthquakes, measure pressure changes at the seafloor, record temperature fluctuations in hydrothermal vent systems, and transmit all of this data to scientists on land in real time. The monitoring is in place and detection is possible. But prediction is not, and that gap between detection and prediction is where the danger lives. Consider what the monitoring system has already revealed about Axial Seamount, the volcano sitting on the Juan de Fuca Ridge approximately 300 miles off the coast of Oregon. Axial is not where today's earthquake swarm is centered, but it is part of the same system, fed by the same spreading center, pressurized by the same magmatic processes. And what the data from Axial shows is this. The volcano has been inflating steadily since its last eruption in 2015. The caldera floor dropped by more than 2 meters during that eruption as magma was evacuated from the chamber below. Since then, fresh magma has been refilling that chamber at a rate that has been closely tracked by bottom pressure recorders and tilt meters on the seafloor. As of the most recent data, the summit of Axial Seamount sits approximately 4 inches, 10 centimeters, higher than it was in the moments before the 2015 eruption. Researchers at Oregon State University, led by volcanologist Bill Chadwick, estimate that Axial needs roughly another 8 inches of additional inflation before it crosses the threshold that has preceded each of its 3 documented eruptions in 1998, 2011, and 2015. At current inflation rates, that threshold will likely be reached sometime in mid to late 2026. We are, by the best scientific estimate available, somewhere between months and a year away from an undersea volcanic eruption on the Juan de Fuca Ridge, and today, the ridge is shaking. Let us be precise about what a submarine eruption at this ridge looks like, because the imagination tends toward images of fiery explosions and superheated steam columns, and the reality is both less dramatic and more extraordinary than that. When magma erupts at the Juan de Fuca Ridge, it does not explode. The water pressure at a depth of 1,400 meters, the approximate depth of Axial Seamount's caldera, is roughly 140 atmospheres, about 140 times the air pressure you feel standing at sea level. Under that pressure, lava oozes rather than explodes, cooling almost instantly on contact with 2 degrees Celsius seawater and forming structures geologists call pillow basalts, rounded, lobate masses of volcanic rock that accumulate on the seafloor like a pile of dark stone pillows stacked in the dark by a force no human has ever watched in real time. During the 2015 eruption, lava trailed approximately 25 miles across the seafloor. 25 miles, the distance from downtown Seattle to the city of Bellevue and back again, covered in fresh volcanic rock, erupted in silence, in darkness, nearly a mile beneath the surface of the ocean. Here is the human scale of what the broader system means. The city of Aberdeen, Washington sits at the mouth of the Chehalis River on the coast of Grays Harbor County. Population, approximately 16,000 people. It is a logging and fishing community, built close to the water on flat coastal land that lies only a few feet above sea level. From Aberdeen, you can drive to the Pacific coast in under 30 minutes. And from that coastline, if the Cascadia Subduction Zone were to rupture in a full margin event, the first tsunami wave would arrive in approximately 15 to 20 minutes. 15 to 20 minutes. That is not enough time for most people in low-lying coastal areas to reach high ground. The residents of Aberdeen wake up in the morning and make coffee and drive their children to school, and they live their lives at the edge of a geological system that the data shows is not dormant. It is awake, it is accumulating stress, and it has ruptured before with a violence that sent waves across an entire ocean. Let us go back to that event, because this is not a theory. This is documented geology. On the evening of January 26, 1700, at approximately 9 o'clock at night, Pacific time, the Cascadia Subduction Zone ruptured. The fault broke along its entire 1,000-kilometer length, from northern Vancouver Island in British Columbia all the way to Cape Mendocino in northern California. The Juan de Fuca Plate, which the Juan de Fuca Ridge had been building and pushing eastward for millions of years, suddenly lurched beneath the North American plate. The slip along the fault averaged 20 meters, 66 feet, in a matter of minutes, 66 feet. That is the height of a 6-story building, moved laterally underground in moments. The shaking was so violent that First Nations people along the coast of Vancouver Island reported being unable to stand. It lasted long enough, geologists estimate 5 minutes or longer, to make people seasick from the motion of the ground itself. The coastal zones of Northern California, Oregon, and Washington suddenly dropped between 1 and 2 meters, drowning the trees at the edge of the tidal zone in salt water. Those trees, red cedars, died that winter, and their outermost growth rings, the ones that formed in 1699, the last growing season before the flood, can still be counted today. They are called ghost forests, and their drowned stumps still emerge from the mud at low tide along the Oregon coast, standing as the most patient testimony in the geological record that this event was real, that it was enormous, and that it came without warning to the people in its path. The village of the Pachena Bay people on the west coast of Vancouver Island was destroyed entirely by the tsunami that followed. There were no survivors in the low-lying settlements. The wave crossed the Pacific Ocean in 9 hours, striking the coast of Japan before midnight on January 27th. Because no earthquake had been felt in Japan, the rupture was too far away, the observers at Kuwagasaki, 300 miles northeast of Tokyo, watched the sea rise and fall with no explanation at all. They destroyed 13 houses and started fires that consumed more. It was not until 3 centuries later that scientists matched those Japanese records to the earthquake in Cascadia. The geology had remembered what the written record could not. That was 326 years ago. The average recurrence interval between full-margin Cascadia megathrust earthquakes, based on 19 identified events in the past 10,000 years, is between 500 and 590 years. The Oregon Department of Emergency Management currently estimates a 37% chance of a magnitude 7.1 or greater event at the Cascadia Subduction Zone in the next 50 years. The USGS estimates a 10 to 15% chance of a full-margin magnitude 9 or greater rupture within the same time frame. Scientists are careful to say the system is not overdue in any simple mechanical sense. Earthquake fault systems do not run on clocks. But the strain that has been accumulating since January 26, 1700 is real, is measurable, and grows with every centimeter the Juan de Fuca Plate advances toward the North American plate. And the Juan de Fuca Ridge, the engine that creates that plate, that pushes it eastward, that has been doing so without pause for millions of years, is shaking right now. Here's the connection that the standard news coverage of today's earthquake swarm will almost certainly not make, because it requires holding 2 scales of time in the mind simultaneously, and humans are not naturally built for geological time. The earthquake swarm at the Juan de Fuca Ridge today is occurring at the divergent boundary, the place where new plate is born. The danger of the Cascadia Subduction Zone is at the convergent boundary, the place where that plate is consumed. These are 2 ends of the same conveyor belt. The ridge creates plate. The plate moves east at 4 centimeters per year. The plate subducts beneath North America, storing strain energy in the locked fault zone at depth, until the accumulated stress exceeds the frictional grip holding the plates together, and the whole system releases at once. When activity increases at the ridge, when earthquake swarms shake the spreading center, when magma moves through the crust, when the system that creates the Juan de Fuca Plate becomes more active, the question of whether that increased activity has any measurable effect on the stress state of the Cascadia Subduction Zone is one that scientists approach with appropriate caution and rigorous uncertainty. But the system is connected. It is one system. The physics of the mantle that drives the ridge also drives the subduction. The plate that shakes beneath the Pacific today is the same plate that is locked against North America tonight. And there is a third thread in this system that the most careful and methodologically precise volcanologists will discuss only in the language of correlation rather than causation, but which the data has consistently suggested deserves attention. The 3 most recent eruptions at Axial Seamount, 1998, 2011, and 2015, all occurred between January and April. This is not a coincidence that has gone unnoticed. William Wilcock, a researcher at the University of Washington, who studies axial seamount seismicity, has noted that this January to April window corresponds to the time of year when Earth is moving away from the Sun, when the planet is at or near aphelion, when the gravitational geometry of the solar system exerts its subtlest influence on the tidal stress of the planet. The Moon's gravitational pull creates pressure variations on the seafloor. The ocean tides rise and fall above these submarine calderas, changing the pressure by measurable amounts. When a magma chamber is already near the threshold of eruption, these tidal pressure variations may provide the final increment of stress that tips the system into failure. The monitoring is in place. The inflation threshold is approaching. The ridge is shaking. And it is April. Now consider the second human story inside this data. The coastal community of Westport, Washington. Population, approximately 2,300 people. Westport sits on a low-lying spit of land extending into Grays Harbor, less than 10 feet above sea level in most places. It is home to a fishing fleet, a marina, a maritime museum. Children go to Ocosta Elementary School there, and that school, because the community understood the risk, was rebuilt in 2016 with a vertical evacuation tower designed to hold hundreds of people above a projected tsunami inundation zone. It is one of the only schools in the United States built specifically so that its students and staff can climb to safety if the ocean rises. That tower exists because someone sat with the data about the Cascadia Subduction Zone and took it seriously. Because the question is not whether this system can produce a catastrophic event. The question is not whether. The question is when, and whether the people in the path of it will have a vertical evacuation tower to climb when the shaking stops. The data from today's earthquake swarm is still coming in. As of noon on April 12, 2026, 18 events had been recorded since midnight, the largest at magnitude 4.2, at a location approximately 250 miles off the coast of Washington state. The Pacific Northwest Seismic Network has confirmed that these earthquakes are not at Axial Seamount and are not at the Cascadia Subduction Zone. They are at the ridge itself, at the spreading center, at the place where this entire geological drama originates. The events, in the words of the scientists monitoring them, are relatively common in this type of setting, and in the 1993 coaxial eruption, the 1996 axial swarm, and the 2001 Middle Valley swarm, the events were also described as relatively common right up until they were confirmed to be volcanic. This is not a condemnation of the scientific communications around today's swarm. This is a statement about the nature of monitoring systems. They can tell you with exquisite precision what is happening. They cannot tell you what it means until after it has already happened. Hydroacoustic data from the Navy's SOSUS arrays and seismic data from the Ocean Observatories Initiative will continue to stream into research institutions at the University of Washington, Oregon State University, and NOAA's Pacific Marine Environmental Laboratory in Newport, Oregon. Scientists will watch. They will note whether the epicenters migrate along the ridge. Migration would suggest a dike injection, magma forcing its way through the crust laterally. They will note whether the character of the seismic signals changes, a shift toward higher frequency content, a reduction in the rise time of the wave packets, would indicate that the source of the earthquakes is moving upward toward the seafloor. They will watch for the emergence of event plumes in the water column above the swarm location, massive temperature anomalies detectable by sensors and eventually by research vessels. And they will do all of this watching from laboratories on land, receiving signals transmitted through fiber optic cables laid on the seafloor, processing the geological equivalent of a patient's vital signs, trying to determine whether what they are seeing is a routine fluctuation or the first sentence of something much larger. What the 1999 Nature paper by Johnson and colleagues showed after studying the hydrothermal system at the Juan de Fuca Ridge in the aftermath of an earthquake swarm of apparently tectonic origin was that vent fluid temperatures did not begin to rise immediately. They began to rise 4 to 11 days after the first earthquake. Then the temperatures oscillated for approximately a month before settling at higher values. The fluid output from the hydrothermal system increased tenfold over a period of at least 80 days, extending along the entire ridge segment. Tenfold. The entire ridge segment. Days and weeks of data flowing in before the full picture became visible. The story of the Juan de Fuca Ridge is a story that rarely announces itself all at once. It tells itself slowly, in pressure readings and temperature curves and seismic frequencies. And by the time the picture is fully assembled, the event is already finished. History is already written in the geology, and humans are left to read it after the fact. And this is the deepest and most unsettling truth inside today's earthquake swarm. Not that this swarm will necessarily lead to a volcanic eruption, it may not. The scientists are correct that such swarms are relatively common and often resolve without dramatic consequence. Not that a submarine eruption at the Juan de Fuca Ridge would pose a direct danger to people on land. It would not, because Axial Seamount is too deep and too far offshore for its eruptions to generate tsunamis or be felt on land. The deepest truth is that the system generating this swarm is the same system that has been generating the Cascadia Subduction Zone's accumulating hazard for millions of years, and that accumulation continues whether or not a particular swarm on a particular April morning leads to anything observable. Every day that the Juan de Fuca Plate continues to move east, 4 centimeters, the width of 2 fingers, is another day of stored energy in a fault system that has not released since 1700, that the geological record shows will release again, and that the cities of Seattle, Portland, Tacoma, Olympia, Vancouver, and Victoria, combined home to millions of people, sit directly within range of. The monitoring infrastructure is extraordinary. The scientific understanding is deep and growing. The evacuation plans exist, and the warning systems exist, and the ghost forests of drowned red cedar still stand in the mud along the Oregon coast to remind anyone who visits them that the warning is not theoretical. It is geological. It is permanent. It is written in the rings of trees that died in a single winter more than 3 centuries ago, because the ocean came for them in the night, without warning, after a machine 250 miles offshore sent a plate of rock sliding beneath a continent. The swarm at the Juan de Fuca Ridge may quiet by tomorrow. The earthquakes may diminish in frequency and magnitude and leave no trace except in the seismic records of the Ocean Observatories Initiative. Or they may be the first signal of something beginning. A dike injecting through the crust, a new volcanic structure growing in the dark at the bottom of the Pacific Ocean, another point in the long geological sequence that has been playing out since before the first human beings walked on this continent. Either way, the machine is running. It has always been running, and the coast of the Pacific Northwest stands exactly where it has always stood, beautiful, exposed, and precisely in the path of what the data actually shows is coming, not if, when. And the only honest thing science can tell us about when is that it does not know. It can detect. It can monitor. It can describe the accumulating energy with extraordinary precision. But prediction, the specific date, the specific rupture, the specific morning when the ground begins to shake and does not stop for 5 minutes, prediction remains beyond the reach of every instrument on Earth. The Juan de Fuca Ridge is shaking tonight. Axial Seamount is inflating toward its next eruption. The Cascadia Fault has been locked for 326 years, and somewhere on the seafloor 250 miles off the coast of Washington, in absolute darkness and silence, the planet is doing what it has always done. It is moving, and nothing we have built, nothing we have measured, and nothing we have named will change what happens when it decides it is done.